So today's presentation is going to be on the use of computer simulation for directional FM pattern studies. But before I begin, I'd like to make a special acknowledgement to someone that I'm sure that most of you know, Merrill Weiss. We contracted Merrill to help us write and file a PRM, a petition for rulemaking to allow for the simulation or to allow simulation to be used for FM directional pattern studies. Merrill really helped dig deep into the FM rules, and he provided us with a lot of guidance. So thank you, Merrill. So we filed for this rule back in early June, and we're anticipating the final vote and approval to be done this fall. So, why do we do this? Well, I'm going to go into a little bit of history, background, and discuss a lot of the benefits of computer simulation has over traditional range measurements. So there are approximately 900 Class A directional FM stations in the US. And currently, the FCC rules for licensing a directional FM antenna say that applications for license upon completion of the antenna construction must include a tabulation of the measured relative field pattern. Well, read literally, this implies that the measurement must be done after installation. Now, this rule was adopted back in 1963, and it's quite impractical, and even more so in 1963, given the test equipment they had to work with to do any kind of field measurements. So, without any changes to the wording in the rules, it was interpreted to mean on a full-scale range before shipment. And, the FCC has since accepted this interpretation. Well, a little more history. In 1976, Matti Sukula presented a paper at the NAB symposium called Pattern Optimization for FM Antennas. And in this paper, he proposed the use of parasitic elements, which are basically metal rods used to push and pull the azimuth pattern as directors and reflectors. And this is basically the Yagi principle. I'm sure most of you have looked on rooftops and have seen Yagi antennas that use rods to directionalize the pattern. So it's pretty much the same concept. In the same paper, he also proposed the use of scale models on the range instead of full-size elements. And this proved to be a lot more economical. Certainly the models were much easier to manage. The scaling factor that was used was 4.4 to 1, and actually that's still used today. The reason is that if you scale FM frequencies by 4.4 to 1, that puts you just below the UHF band and above the VHF. So again, here we see a case where without any changes to the wording in the rules, it became another acceptable method for pattern authorization by the FCC. So now it's been 58 years and basically nothing has changed in the FM rules or the measurement process to validate FM patterns. And it's interesting that aside from FM, the commission does have a history of accepting computer modeling. And basically, the way that antenna patterns are handled in general have evolved in all of these other FCC services. AM broadcast, for example, in 2008, the rules were updated to allow the method of moments for pattern verification. And, if you look at the rules for TV and RF exposure, they're already really flexible enough to permit computer modeling. So basically, in a nutshell, FM is the only service left with the burden of building physical models and collecting measured data. So let me take a minute to talk about how computer modeling impacted Repack. Repack was pretty unique, had a very aggressive timeline. And in order to reduce lead times, we replaced modeling, physical modeling, with computer modeling. And since 2017, when we did that, we have shipped over 1,000 antennas, which were based on just virtual designs alone. So to give you an idea of what the physical modeling looked like in our lab before switching to simulation, here's a short video on the top of your screen, which shows a full-size model being assembled. In this case, it's a slotted coaxial antenna, which we had to set up with adjustable features such as adjustable slot shorts, as you can see being put in there, and different coupling sizes. So this was a long, tedious process. After that, we had to make changes to the slot length and the coupling and record amplitude and phase differences and impedance differences. And it took approximately 500 measurements to collect enough data to design the full antenna. So, as you can imagine, this process was pretty lengthy, and switching to a virtual environment really reduced lead time. We were able to reclaim some much needed manufacturing space, and it proved to be more accurate because what we saw is that the test times of the actual manufactured antennas were much less after using simulation than they were using the data from physical models. So I think it's basically safe to say that it would have been impossible to design and manufacture all these antennas that were needed for the Repack without computer modeling. And another fallout of the Repack is that we were left with a new crop of engineers, which I call now HFSS super users, and new opportunities such as FM pattern simulation can take advantage of their new expertise. So I'll talk a little bit about the limitations of actual range measurements and the benefits of computer modeling. If any of you ever done range measurements, you know how difficult it is to accurately measure radiation patterns on a range. Things like alignment between the source antenna and the receive antenna rely on just mechanical bore sighting, which is never perfect. No range is truly in free space. You always have reflections from, the ground, trees, the test setup itself. And there's also a lot of I call RF spam floating around out there, which causes external interference. And all of these things, they really limit the accuracy of any range measurement. And that can be removed with computer simulation. Computer simulation, it also eliminates lengthy setup and takedown times of models. You can see a picture here on the bottom of your screen, which is a scaled model in our test range. And what I can tell you is that over the years, our technicians have become experts with aluminum tape and tie wraps. And once the geometry is set up, they had to record by hand the information such as, where is the radiator in space, where are the parasitics in space, and all the dimensions of all the parasitics and so on. So these are all sources of error. With computer simulation, once the geometry is defined, the computer model can just simply be exported into CAD drawings. So it's kind of like replacing old timers arts and crafts with modern technology. So now I'm going to touch on the significance of polarization ratio. The current FM rules state that the supplemental vertical polarization ERP shall in no event exceed the ERP authorized. Well, the ERP authorized is a horizontal polarization. And broadcasters, they consider the V pole more important than the H pole. I would debate that today, since FM antennas that are hidden in vehicles are usually in the windshield and the bumper. and they really are. They're horizontally polarized. But broadcasters, they still tend to maximize the V-pole. So, this makes the polarization ratio measurement important because we want to make sure that it complies with the rules. Accurately measuring HV ratio is very difficult. As I said, no range is reflection free, and the fact that horizontal and vertical waves, they reflect differently. This all limits the accuracy. Also, you have to ask the question, are the H-pole and V-pole patterns coming from the source antenna the same? If there's any beam tilt on the source antenna, as you rotate that antenna from horizontal to vertical polarization, that basically creates a wobble, which again introduces error into the measurement. So it's a tricky measurement for sure, and this all can be eliminated. All these possible issues can be eliminated and removed with computer simulation. Another huge advantage of designing a virtual environment is that it really does lead to complete optimization. The process is not compromised by time constraints. You don't have to settle for, well, it's close enough. Software can very efficiently make small tweaks to the geometry, and much better optimization. Basically, optometrics replaces trial and error. And by establishing certain criteria, like the FCC footprint, percent of null fill, pattern fill, which the rules require 85% fill. Criteria such as the V-pole has to be less than the H-pole, and certainly the end user has directions of interest for the pattern. And from there, artificial intelligence can really make some smart decisions outside of the software by simultaneously solving a lot of combinations of the parasitics and the pattern shapers and radiator location and direction. So what I like to do now is take a look at a comparison between a range measurement and simulation. And for this comparison, the physical model is done at the 4.4 to 1 scale. The bay itself, the antenna, the tower, as well as the frequency, all scaled. And the pattern is measured in an anechoic chamber with the source antenna placed at one end and the antenna to be measured placed at the other end. The computer modeling, this was done with HFSS, which is an ANSYS product. It's basically a 3D electromagnetic simulation tool. And we use this extensively for designing all of our antennas, RF systems, our components, as well as we do radiation studies, such as near-field drone study comparisons as well. So once a model is drawn, the software applies a mesh over top of the model, and Maxwell's equations are more or less solved at every node. We have had full-scale models that have had over 2 million nodes. So you can imagine that you need a lot of computing and solving power to do this. But with a tight mesh, it's therefore really not an estimate, but almost an exact solution. So in order to do a comparison, we need a figure of merit. And what I use is a correlation coefficient. It's a good tool. It basically tells you how close two sets of data are. A correlation of 1 shows a perfect match. A correlation of 0 means that the two sets of data are not related at all. Here's an example of a study done actually in Wisconsin, WHEM in Eau Claire. The original range measurement was done in 2014. And on the right is a picture of the scaled model showing the parasitics. And what we did was we recently replicated that final geometry in HFSS, which is the model that you see a little bit to the right of the photo. The results of the pattern comparison that they're shown to the right. You see both the H pole and the V pole, where the green was the FCC Protect, the blue is the HFSS simulation, and the red was the actual pattern study done on the physical model back in 2014. What you can see is that the results, they match pretty closely, with correlation coefficients of 0.986 for the H pole and 0.96 for the V pole. So again, very close. One thing that I would note is that if this study was done today, we would have tweaked it a little bit more, since the V pole lies slightly outside of the H pole, or outside of the FCC Protect. But, you know, we did the best we could with the tools we had at the time. So because we believe simulation is much more accurate than any range measurements, examples like this are really, in my mind, just an exercise to validate how good the range measurements are. They're not to validate the use of simulation. So some conclusions here. We've got 58-year-old rules that still require FM manufacturers to measure the physical models for FM directional licensing. And, you know, we've seen for decades, computer modeling has evolved in all other broadcast services except FM. And, you know, we believe we've shown that simulation yields much superior results compared to traditional range measurements. It is more reliable because they're performed in a truly free space environment. They eliminate such issues as mechanical tolerancing and human error. And computer simulation really does allow the geometry to be completely optimized. You know, you can run literally hundreds and hundreds of simulations in a much shorter time than you can physically make adjustments to a model. So you're not compromised by time. And so in short, what I can say is that this rule change is long overdue. So with that, I will take any questions that you may have.